depending on where you learned about functions first, or even reviewed it a couple times, there may be a little different emphasis on how much was placed on what a function is and what the terminology and how you describe certain characteristics about a function. And this is going to be a huge part of this course, is talking about functions and making descriptions of what the domain and range are and what graphs look like and things like that. So we're going to start out with looking at what a function is, what the terminology that we'll use with it will be. Okay, so I have a definition, and it's a rather long one, but it's an important one. And so depending on what textbook you look at, there's different kinds of definitions, and this is one that is hopefully plain English enough to make it understandable. A function is basically a rule that takes an input, an independent quantity, and it assigns it to an output. Okay, and we call that the dependent quantity. And the most important characteristic of a function is that one input is assigned to exactly one output. Okay, so this is, you may have the same output for several inputs, but for any given input you have exactly one. And this is a little bit like what we were talking about on Monday, where I think we mentioned it on Monday, where we were talking about the height of the president, that his height can change or it can be the same at different times in his life, but at any particular age he's exactly one height, right? It wouldn't be, you wouldn't expect somebody to be two heights at once, although in different times in their life he could be at the same height. Now I will post these notes, and I am recording this, so you'll have it on Moodle afterwards if you need to go back or whatever, and hopefully this will work out to be a good system for keeping up with the class. So if I go a little bit too fast, please slow me down if it's fast on the explanation. Occasionally there's a lot of writing involved, so you can count on having the notes and going back and filling in your notes if there's too much to write down at once. Okay, so the way we talk about it is the output is a function of the input, or something like this in the homework assignment, where we talked about the tide is a function of the time since the last low tide. Okay, so the output, which is the tide height, and the input, which is hours since the last tide, we'd say that the height is a function of the time. Okay, I already answered this question, I think, just in what I said. Is height the function of age? Yes, at any particular age you're a particular height, but then age is not a function of height. Just because I'm 5'11" or 6 feet doesn't really tell you anything about my age, even if you had a graph of my age versus height, because perhaps last year and the year before that I'm the same height that I am right now. Okay, so what about this? Is price a function of an item? So I tell you an item, you have a price. Assuming we're in one store, would that be a function? Would be, right? But then is the item a function of price? So if I say $2.99, would that tell you what item I'm talking about? Usually not, right? I mean, you can construct a circumstance where it might be, but usually not. It's fine to and expected in stores to have several things that have the same price. Okay, so is your test grade a function of your score? You would hope so, right? And then the other way around, is your score a function of the test grade? Not really, because it could be any given value. So if you have an A, you could have had a 94 or a 96. So there's more than one number associated with the letter grade. So this is more or less a step function where there's a range of values, and I use that word probably incorrectly, but there's several values that correspond to a single output. Okay, so let's have a definition here. A one-to-one function is a relationship or a function where each input corresponds to exactly one output. So it is possible that we have these functions that go both ways. So when I tell you what the input is, you can find what the output is. If I tell you what the output is, you can say what the input is. And if you do have that kind of relationship, we call that one-to-one. And so, okay, is the weight of water a one-to-one function of the volume of water? So in other words, if I say I have 64 pounds of water, could you tell me how much volume I have? I mean, assuming you have a table or something, or knowledge about how much water weighs, you would say that if you have 64 pounds, that's about 1 cubic foot. So if I do it the other way around, okay, is the weight of a person a one-to-one function of his height? And certainly not, right? Because I could be the same weight for many different ages. So I'm at my weight right now. A year from now, I may or may not be at the same weight. So that wouldn't be one-to-one. But something that has a physical constant to it, like water, if I told you the volume of water, if I say 1 gallon, you could tell me that that was 8.48 pounds. And so that is a function, that's a one-to-one function. Weight of a person is not. Okay, anybody think of one that would be an example of a one-to-one function, perhaps differently than what I'm suggesting?
Celsius to Fahrenheit?
Excellent. That's right. When you're at I can't convert really quickly in my head, but about 70 degrees is about 20 centigrade, right? Celsius. So when you have one particular temperature in one scale, it's exactly the one temperature in the other scale. Good. Okay, so let's talk about the symbols of how we do this. So if we say distance is a function of time, what I'm going to ask you to do when you're doing these things is to be very careful about how you define letters. Now we're going to have, symbols for functions and and symbols for variables and things. And so I'd like you to define that, because occasionally, as you get a little bit later in calculus, you'll be using functional notation without necessarily its argument. So f could be a variable or a function. So we would write it as in parentheses, like if distance is a function of time, we would say d at t or d of t is the distance. And in this case, you could make a reasonable assumption, if you weren't familiar with the fact that we're talking about functions, that this would be d times t. And so that's why the definition has to be, stated, where you're saying whether you have a function or whether you have just a multiplication. So be very careful about that, and always define your variables. Put the units if you can. State if it's a function or if it's just a variable. Okay, so there's 4 ways really to define a function. We can define it verbally, like I can say I'm 5 years older than my brother, or 3 years older than my sister. You can have a table that defines a function, right? You've all seen tables where perhaps you're looking up a price list or something of that sort. With graphs, I've been showing you some graphs that are functions, and we can also make algebraic expressions as functions. And so the notation of the function would stay the same. We would still say d at t, but it could refer to any of these things, a verbal rule, a a graph, an algebraic expression, anything like that. We're going to deal mostly, though, with algebraic expressions and, to a lesser degree, graphs. Okay, so let me make a quick graph or a quick table here of a relationship between age and weight. And so when I say if W at A is the function of weight as time, W at 10 would represent what? You just, somebody said it already? What's that? Yeah, weight at 10 would be the interpretation, and so what would that be then? That's 70. Now what's implied in the table is that perhaps there's intermediate values, and you certainly would expect at 10.5 you would be a certain weight, but that's not always the case. You can have functions that really only relate 5 values, but in this case these are representative values. Okay, so if we're looking at the weight at 125, what is A then, and what does A represent? It's the age, and that would be 15 then, right? Okay, so let's talk about some new symbols here. I'm going to say A is 10, and delta A, which means the difference in A, is 5. Okay, so if I say delta W over delta T, what I'm going to define that to be is my weight at an age plus delta A minus the weight at that age over the difference in age. And so what does this mean now? All right, so if we look at W A plus delta A. So I've already defined A as 10, and so delta A is 5, so we're going to say this is 10 plus 5. And then the second one is the weight at A, which is 10, and then delta A is 5. So what is this going to mean if I have W at 15 minus W at 10 divided by 5? What would that represent? What did I just calculate? Anybody want to venture a guess? Yes?
It's a guess, but is it how fast they're growing?
Exactly, yeah. It's the change in weight over the number of change in years. And so if we evaluate these things, W at 15 is 125, and then W at 10 is 70 over 5. And so here we have, what is this, 65? 55. 55 over 5, which would be 11. That would mean that between the ages of 10 and 15, there was an average weight gain of 11. Oops, that was a little too fast, sorry. Okay, so it means, very simply, that's the average rate of change. Now this difference that you see here, it looks like a pretty complicated formula, but get used to it, because this is exactly the same as y2 minus y1 over x1 minus, or x2 minus x1. You know, we're looking at essentially the slope or the rate of change between two values. And we're going to start expressing it like this more than doing the differences in y's over the differences in x's. But the meaning is the same.
Wait, so what is the formula for, like, without the W's and A's?
Well, there's no, the way you'll see it, I guess, in a generalized sense, will be using F, right? And so you would have and so this is your average rate of change. And we call that the difference quotient. And I'll be coming back to this pretty frequently. In fact, this is going to be a very common expression in this class. Okay, so let's talk a little bit about graphs. And there's any number of ways to make graphs, and if you look in the newspaper, you'll see really, really great and really, really terrible graphs. USA Today in particular is known for making graphs that don't make really good sense. They like to make very colorful ones, but sometimes they're very confusing. But by, I guess, by tradition or by convention, we usually use the horizontal axis to show the independent variable, and then the dependent variable, or the dependent variable, excuse me, is on the vertical graph. And so if we look at this particular graph that I've drawn, x is the independent variable, and y would be the dependent variable. So that means it would be like answering the question, what is the value of y? And you would say, well, choose an x. And if I chose an x, I could tell you what the value of y is. And so it's usually x is the one that's to be chosen. That's your independent one. And then y depends on the value of x. And that's where that whole independent, that's the one you choose, the dependent one, depends on what you've chosen in x to give you that value. Okay, so let's look at a few graphs here. Here's a line, a curve, and a circle. They're all perfectly good graphs. So which ones are functions of these three? The first two. Yeah, certainly the first one, that's a line. A line is always a function because I choose any x and I would get exactly one y. Second thing with the, the second graph, I can choose any x and I'll get exactly one y. But certainly with the third one, if I chose, let's say, an x that would be somewhere here, I would have two y's that correspond to it. So this one would not be a function. Now, which ones are one-to-one? Okay, that means that there's exactly one value of y for any value of x, and there's exactly one value of x for any given value of y. And so in this case, then, the first one would be one-to-one, because if I chose a y, there's only one x value that's associated with it. Now this one, if I look at y equals 0, I have three different x values that correspond with that. And certainly it doesn't make sense to talk about a one-to-one function with a relationship that's not a function to begin with. Okay, so what we're going to use is the vertical line test to tell you if you have functions, and then we're going to use the horizontal line test to determine if it's a one-to-one function. So it's just kind of a way to visualize. With the vertical line test, you choose any x, and it should cross over the curve exactly one spot. That'll give you your one value for y. The horizontal line test will tell you that for any given value of y, you only have one value of x. And if you have more than one value of x, then you don't have a one-to-one function. Okay, so algebraic expressions are, you generally perhaps don't think of them as functions, but some of them we can convert into a function. And you'd want to do this when you have a relationship that maybe has some physical meaning or so. And here I'm just choosing two arbitrary variables, n and p. And we can say, if we designate n the independent variable, then that makes p the dependent variable. And so it really comes down to, if you have a relationship, if I ask you, what's the value of p, the answer would be, well, it depends on n. because you can choose n and you'll get a p out of this. So what you do is you make a decision based on the model. So these relationships, for example, the relationship between temperature in Fahrenheit and Celsius, you can make the function go one way or the other. If I give you Fahrenheit, you can give me Celsius, or the other way around. If I give you Celsius, you can give me Fahrenheit. So what you can do then is instead of treating p as just a variable, we can talk about p as a function of n then. And so in the first line that I showed you, 2n plus 6p equals 12, you think, okay, n and p are variables, but we can restate it just by rearranging it, that we have now a function that we've defined, p at n equals 6 minus n over 3. These two things describe the same line. This is, of course, a line when you have n on the horizontal axis, p on the vertical axis, and this is a function that is exactly the same line, but it's now expressed as a function. Okay, so why don't you try this one? What I'd like to do is turn this into a function A whose independent variable is b. So I want A at b is what I want. So you'll have to rearrange this somehow to make this function. So I'll give you a couple minutes to do that. So let's go with this then. And so what I'm going to do is first thing you want to do, if you want to isolate an A, which is what we want to isolate, is that we put all the instances of that variable on one side of the equation, everything else on the other side of the equation. So the 3a and the 4ab I'm going to keep on the left, and I'm going to subtract 2b from both sides, and I'll get it on the right. And then I can factor out the a, and then it turns out that my a is simply 7 minus 2b over 3 plus 4b. And so now I can declare this a function because this works out, really nicely. And so for any value of b now, I can determine my value of a. All right, now not every function, not every equation can be made into a function. And this happens when you have functions that are not one-to-one. And so what you occasionally find is that there will come a time in doing your algebra where you're going to end up with something that is ambiguous. And what you'll see mostly is when we have a square involved. And so if I look at a circle, the standard form of a circle is x squared plus y squared equals 1. So that's a circle with a radius of 1. If I want to make this y a function of x, I try and do this. But if I do this properly, when I take the square root of y, I'm going to end up with plus or minus the square root of 1 minus x squared. And so this cannot be a function the way it stands right now, where I just say, okay, for any particular value of x, I'll get 2 values of y, or up to 2 values of y. It's possible to get a single value, but in this case we only get, we usually get 2 values. So I think this is what I just said. So the condition we're looking for here, if we want to make a function out of an algebraic expression, is to make sure that the function is, or that the relationship is 1-to-1. So it's helpful when you look at functions and say, okay, this function is a 1-to-1 function, and then you can actually make a this kind of relationship. Okay, so let's go on. Are probably useful since I just mentioned a circle. This, and I apologize for this being really small, and I'll rewrite what I have on the board for those of you in the back here. The distance formula is something that you should be quite familiar with. And then the equation of a circle, which you can see like this, where the radius equals the square root of y minus k squared plus x minus h squared. Several ways to write this. Perhaps what's a little bit more familiar is writing it like this. I think the textbook that we use in Math 12 has it like this usually, where h and k are the center, and that r is the radius. And if you compare these two forms, they're actually the same equation, where what this is saying is that at h and k, this represents the set of points that are a certain distance away from that point h and k, and that's what this, of course, tells you too. If you take 2 points, you get the distance between them. And so that's that is the definition of a circle, is that it's the set of points that are the same distance from the center. Okay, so I'm going to try and keep the writing a little bit bigger for you, especially in a larger class like this. All right, so the next thing we need to talk about in our discussion of functions is domain and range. Now, the domain and range, they're not, in the sense that we use them for a function, is not really part of our normal everyday speech. So you have to kind of keep in mind what these words mean. Domain is an unusual enough word where that's an easy enough definition to make. That's the set of all input values in a function. Now, it's easy to talk about range, and earlier today I used the word range, but not in this sense. The range when we're talking about domains is that's the set of all possible outputs. Okay, so if we have our function f at x equals y, okay, so x, all the permissible values of x are the domain, all the permissible values of y are the range. So it's helpful to write these things in several different notation forms, and you're going to discover on your homework assignment on web work that some questions will ask for sets in set builder notation, some will ask it in interval notation, some will ask just to write an equality. So to review what set builder notation is about, it looks mysterious, but it's actually probably the easiest way to describe a set. What this comes down to is this, this brace here literally translates into the set of. And then we have an arbitrary variable. We usually use our independent variable. And so we say the set of x. And then this line, this vertical line here, just means such that. And so really with this framework of the set of x such that, it really leaves you a lot of freedom, because then you just make a list of all the things that you want to include here. Or exclude, sometimes that's a little easier as well. So we have this particular set builds up, so we read this as the set of x such that x is between 0 and 1. Okay? Now oftentimes we'll just write domains as the inequality, and that's okay sometimes, so long as we're clear about what we mean. And then we also have set notation where, or excuse me, interval notation, where this would be written as as that with the square brackets. So the thing to remember about interval notation is that when you put parentheses for your intervals, you have, that excludes the endpoint values. When you put square brackets, that includes the endpoints, and you can mix these. One side can be a parentheses, the other side could be a bracket. Okay, so let me do a couple examples here where I'll show you in three alternate ways to represent the same set. So the first one is if we go from, if h is between 5 and 10, and it can be including 10, we would just write that inequality in the set builder notation framework. So we have the set of h such that, and then we make the inequality and close it off. Or we can write it as an interval. If we just have, let's say, h is less than or equal to 10, we just put that exact same thing in the set builder notation. But here with the interval notation, we have to introduce a negative infinity. And negative infinity always has the parentheses there, never the square bracket, because it's negative infinity means that it decreases without bound. It doesn't refer to a specific number, right? Infinity is not a number. It's a concept that says that these values increase without bound. On the other end, if we want h is greater than 5, set builder notation, we just drop it in where the description happens. And then with the interval notation, here we use the parentheses because we're not including the 5. And then we put infinity on the other end with a parentheses again. The difficulty with interval notation is that it depends on the context that you're using it. You know, if we have two numbers, like the first one, well, that's 5 with a square bracket. But if this were to be just 5 to 10, not including the 10, you know, what does that mean? Is that a coordinate pair or is that an interval? And depending on your context, it could change. So even though it's nice and compact mostly, we have to be clear again on its context, that we're referring to the interval and not the coordinate pair. Now, if we have all real numbers, we can say, you know, that h is just h, right? It can be greater than negative infinity and less than infinity, and that's essentially what interval notation says. And sometimes in set builder notation you'll see this, and I don't expect you to come up with this. I don't think there's any reason for us to use this here, where we say h and then this funny looking e means is an element of, and then the capital R with that line is the set of real numbers. I guess when I was talking about sets of numbers on Monday, I really didn't say what those letters meant. We can, so there's the way you would read it. We would simply say R as being the set of real numbers. Okay, so that's a perfectly good notation. This means the set of real numbers. So if I ever ask you for the domain and the range or a range of a function where the domain is all real numbers, this is a perfectly good and a complete way to describe the set of numbers. Probably the other one that we'll see, that you'll come across, perhaps not in this course though, this one is the natural numbers, the set of natural numbers, and then a z, which comes from some mysterious German word, means integers. And those are the three most common ones that you'll see. We're not going to be using these two because most everything that we're doing in this class involves you know, continuous numbers that can be any real number, rational or irrational. When you get into things like sequences and series, you'll start to see the set of natural numbers and things of that sort. Okay, so if we're going to represent more than one set or more than one interval, we use this, this funny looking U. If you see it written in a printed page, it's not quite the same font that you would use. It's really just a line that looks like a U. We use that to mean the union of several intervals, and so if x can be between 1 and 3, or x is greater than 5, in set builder notation we would just use the word or. Nothing wrong with that, okay? In interval notation you would make your intervals and you would put this U in between them, and that means that we're talking about a set that includes all these possible numbers. So if we're talking about x being in that set, we're not talking about it being in both intervals at once. We're talking about it possibly being chosen as any value in those sets. Okay, so here's one. I'm going to just draw the number line, and you come up with the interval notation that describes that. Okay, so write that in interval notation. Okay, did you get something? Anybody want to describe what they got? It's a question of using parentheses and brackets. So the notation on the number line shows you where to use the parentheses and where to use the square bracket. And so if we were to write this out, we get, in set builder notation, we would just write it like that, or in interval notation, which is really what this is about here, is we would go negative infinity to negative 1, and it would include the negative 1, so we have the square bracket, and then the union with 0 to 3, and we're including the 3. So set builder notation, you can see, just has this framework where we say the set of x such that, and then we just make our description with inequalities and ors and ands and things of that sort. Interval notation, it starts to look a little bit very, I don't know what the word I'm looking for is, but it looks very mathematical, I think, you know, when you start to have a lot of symbols that don't necessarily flow off the tongue so easily. All right, now I'm getting into really, really small writing. And what I want to talk about are something called toolkit functions, and we'll be getting into this later. And so I'm going to stop here.